Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on January 27, 2026, about 6 days ago. It introduces a method called Self-Distillation, fine-tuning, that allows models to learn directly from demonstrations in an on-policy manner, achieving 89% accuracy on knowledge acquisition tasks, compared to just 80% with standard methods. The paper is titled, Self-Distillation Enables Continual Learning. And as we'll see later, the results for sequential learning are particularly impressive because they manage to avoid the usual reasoning collapse found in other approaches. So, Figure 1 illustrates the trade-off between learning new skills and remembering old ones. The vertical axis tracks performance on prior tasks, while the horizontal axis measures accuracy on a new task. Standard supervised fine-tuning, shown here by the orange path, improves new task accuracy but causes a sharp drop in prior performance, which is the classic catastrophic forgetting problem. However, the proposed self-distillation fine-tuning method, marked in blue, moves the model to the top right, essentially mastering the new task while keeping previous capabilities intact. Alright, Figure 2 breaks down the mechanism behind this result. The left panel shows the architecture where the model plays two roles, a student that sees only the query and a teacher that sees both the query and an expert demonstration. The training objective minimizes the divergence between them, distilling the teacher's in-context insights directly into the student. Then, on the right, the contour plot illustrates why this prevents forgetting. The teacher's distribution remains much closer to the base policy than the raw demonstrator does, ensuring updates stay within a safe trust region. Well, having established the mechanism in Figure 2, Figure 3 demonstrates the impact on sequential learning. Here, a single model is trained on 3 tasks, one after another: tool use, science Q&A, and medical reasoning. In the left panel for self-distillation fine-tuning, look at the light blue line for tool use. It stays high and stable even as the model shifts focus to learn the subsequent science and medical tasks. By contrast, the right panel shows that standard supervised fine-tuning suffers from severe interference. As soon as training shifts to the second task, performance on the first one collapses, creating a failure pattern that cannot accumulate knowledge. Okay, while the previous figure focused on skills, Table 1 shifts to knowledge acquisition, testing how well the model integrates new facts. First, notice that the base model scores 0 across the board because this information is completely new. Continual pre-training, labeled CPT, also struggles significantly, reaching only 9% strict accuracy. In contrast, look at the bottom 2 rows. Supervised fine-tuning improves to 80%, but the proposed self-distillation method surpasses it with 89%. Crucially, the final column shows 98% out-of-distribution accuracy for the new method, confirming it truly internalizes the knowledge. So Figure 6 investigates whether the performance boost comes from the teacher's quality alone or the on-policy learning process itself. The chart tracks accuracy over generations for 3 different approaches. The dark blue line at the top represents the full-on policy distillation method, which consistently leads the pack. In contrast, the lighter lines show offline alternatives, like simply imitating teacher samples. This gap confirms that on-policy generation is essential, because the offline methods plateau at much lower accuracy levels, despite using the exact same teacher. Alright, Table 5 details the exact numbers across 3 scenarios: science Q&A, tool use, and medical reasoning. Focus on the top section for science Q&A. In the new task column on the left, self-distillation fine-tuning leads with 70.2% accuracy. However, the average column on the far right reveals the real difference. While supervised fine-tuning drops the average on prior tasks to 53.4%, the self-distillation method holds firm at 64.5%, proving it avoids catastrophic forgetting. Wrapping up, 2 takeaways stand out. First, we can achieve robust on-policy learning without explicit rewards just by leveraging the model's own in-context abilities. Second, this approach effectively solves the catastrophic forgetting problem, making lifelong learning for foundation models a real possibility. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.